Physics is me, you, and us. Why do we study it? How can we understand quantum mechanics, relativity, the Big Bang Theory, and our universe? All of this and more are discussed by Dr. Nassim Magdi at the YouTube channel Nesentron.
Hi everyone, I would like to welcome you for a new interview about a very interesting topic in relativistic heavy ion collision. Most of us are familiar with the concept of causality in physics and in quantum physics especially. And there was highlights recently about can collective excitation expand faster than the speed of light? And that's raised many questions about the causality in quantum mechanics and causality in relativistic physics. So today we had one of the authors, we had Dr. Lorenzo, to tell us about the paper, but we will start by introducing Dr. Lorenzo to us first.
Dr. Lorenzo Gavassino. Postdoctoral at the Department of Mathematics at Vanderbilt University. In 2022, he received his PhD in astronomy and astrophysics at Nicholas Copernicus Astronomical Center in Warsaw. His work covers various topics in physics, including relativistic fluid dynamics, relativistic kinetic theory, and relativistic quantum mechanics. Dr. Lorenzo will discuss his recent work today and try to answer the question: can collective excitations expand faster than the speed of light?
Lorenzo, welcome to the show.
Thank you very much. It's a pleasure to be here. I'm very glad that you're interested in our work. I hope we will manage to deliver some ideas. It's a rather technical result, but we will try to make it as simple as possible.
That's the point we try to do. And as I know, you're a postdoctor in Nashville, in Tennessee. So we're both at the same state. Basically, your work is focused on relativistic nuclear collisions in theory, let's say called theoretical. However, before we jump to that, let me ask you a general questions about you first.
Sure.
Why do you like physics? What's interests you to do physics in general?
Mm-hmm. Yeah, so as a child, I've always had a lot of fun imagining things. I was imagining stories, adventures, entire different worlds. Was walking through the house for hours imagining an alternative reality and all possibilities. And then I discovered something very interesting. Mm-hmm. I discovered that in physics, when people write down the fundamental equations of a theory, these equations contain an infinite number of stories, an infinite number of words and possibilities. If you give me the Maxwell equations of electrodynamics, those contain, electromagnetic waves. They contain the atom, if you quantize it also, it contains all possible different situations and stories. And for me, the fun is really to write a paper and through this paper discover a story. For me, every paper is an adventure. And the incredible thing is that when someone writes down an equation, it contains all these infinite stories, but these stories are not in the mind of the person who wrote the equation, right? When Einstein wrote down the equations of general relativity, he didn't know its solutions, right? The true solutions. He didn't know they would lead to black holes and to all the amazing things that appeared later. So the equation contains an infinite amount of information that is not in the head of the person who writes it. Mm-hmm. So there are all these stories that are just there that wait to be discovered. And for me, the fun is to imagine these stories and, if you want, experience these stories in my head. That's the essence.
That's an interesting story. And I started my journey as a theoretical physicist and then switched to experiment. As we work right now at relativistic heavy ion collider. And as you said, I always look to these equations and wonder, when someone writes an equation, what they had in mind. And when you try to do that yourself, you write the equation and look at it, and it describes something, but can you learn more? Does it represent what you want or more than what you want some of the times? As you said, Albert Einstein write the equations for general relativity, and then black holes comes later, gravitational waves, and too many things comes out of it.
Yeah, but because an equation contains infinite information, right? I mean, all the solutions are an infinite amount, and you cannot contain all that knowledge in your head. And so people keep discovering stuff after you wrote those equations. And actually, it's really fun to read the original papers of Einstein, Planck, Schrödinger, because you see that they arrived at those equations with a completely different pattern in their heads with respect to us. We are presented with the final thing, right? Everything well prepared for us to appreciate it. But the process that leads to an equation is pretty chaotic. It goes through a lot of trial and error. It's a very interesting process.
Yeah, I think this one thing you highlight over here that's maybe non-physicists will not know, that it's not the equation itself. Sometimes it's a solution of the equation. How many solutions you can have to one equation. So you have a general equation, and this equation could have many, many solutions that all deliver a lot of physics inside. And that's one thing.
General relativity is an equation that allows you to write down the structure of universes, right? So it contains worlds. It's amazing if you stop thinking about it. If you stop and you think about it, stop. It's amazing. Yeah,
that's so great. And since we spoke about general relativity, I think in special relativity we had the speed of light as one of the universal constant. I think it started over there, getting from Maxwell equation to special relativity, and then in general, by time for general relativity, we know that the speed of light is a universal constant. Nothing inside the space-time moves with a speed that's faster than the speed of light. That's a limit, universal limit. That's assumption.
Yeah. Well, there are some subtleties in that. Okay. Yeah.
Like to hear from you. Yeah, go ahead.
Absolutely. So here you're referring to the principle of relativistic causality. So first of all, let's discuss how it came about. So the historical foundation is that because in relativity there is this phenomenon called the relativistic of simultaneity, which tells you that two events that occur at the same time for one observer, they may occur at different times for another observer. If I now snap my fingers at the same time, okay, you see them occurring simultaneously. But if someone is moving very fast, they may see. Okay, I don't manage to. Okay, they will see. So they will see things in a different chronological order, right? In principle, you can have that the same two things happen, one before and the other after, and then for someone else the order is reversed. So so what happens is that if you can send messages faster than light, then there is a trouble because the chronological order between emission and transmission of the message can be reversed. So we send a message to the aliens, it travels across space, time, it reaches Andromeda Galaxy, and they receive it. Okay. Now, if this message goes faster than light, you can always find an observer that runs fast enough to whom the message started in the Andromeda Galaxy with the aliens, and it traveled all the way to us. So the question is, who sent the message, right? Because who started the whole thing?
The causality will be broken.
Exactly. This is the term of causality. Now, it must be said that technically this is not really a contradiction. It's not really a logical issue. It's just, a paradox of intuition. It's a situation that is hard for us to interpret. But it was considered powerful enough as an idea to just assume that this event cannot occur, right? Let's just assume that we cannot send messages faster than light. And then what happens is that this assumption was put inside the standard model of particle physics. The mathematical structure of the standard model contains this assumption. So eventually, the main reason why we care about this principle of causality is not that it is foundational for special relativity. It's that if something violates this principle, which is something we don't have evidence yet, but if something violates this principle, then this something must necessarily comes from outside the standard model of particle physics. And so it's new physics with respect to the one we know. So this is the historical foundation and the logical mechanism why we care about causality. We care about causality because it's inside the standard model. And so if we want to describe things that exist within the standard model, we need to put it there because it's there. Now, the question is it what is this about? It is not about propagation of particles. You know, the principle of causality doesn't tell you that particles cannot move faster than light or energy cannot move faster than light. The principle of causality tells you that information cannot move faster than light. I cannot send messages. Now, there is a very precise mathematical definition of information, which is the one that enters in the standard model and that enters in relativity. Information is the ability to distinguish between two different situations. So imagine that I have a box that contains a ball that can be red or blue, and the box is completely sealed. You cannot know its color. As soon as you open the box, all the waves, all the information, all the photons and everything that are emitted from the ball propagate across space and time. And the information is the ability of a detector to notice, to be able to say it was blue or it was red, right? So in order to be able to state the principle of causality, you need to imagine two alternative situations that are identical everywhere except in a location. And then you let these two situations evolve, and you see how the difference between the two situations travels around. And that's the statement of the principle of causality.
Okay, and then we assume that difference or this information could not travel more than the speed of light.
That's inside the fundamental laws. Is inside the standard model and not the laws that you construct out from it. It's also inside the general relativity, but with some technicalities. So yeah, that's the statement.
So for my own clarification here, it's very interesting. So yeah, but we also say that information had to be carried, as you said, with some object, the two balls in this case, in the case you have to describe. And then objects that we know locally transfer as are moving with their own speed if they had mass, was with the speed of light if they're massless.
So, okay, so this is a very delicate thing because you need, first of all, to define what you mean by object and what you mean by moving. Because if you are in a quantum world, then you can assign to an object a wave function, for example.
Yeah, which is defined in space-time. So
yeah, so the typical. So imagine a wave function that is a single particle state that is a superposition of momentum eigenstates and so on. Then what you can show, you can demonstrate it. It's a known fact that if you prepare the wave function in a localized region of space, it goes outside the light cone in infinitesimal time. It goes everywhere immediately. Now, the tricky point is that we don't detect the wave function. In quantum field theory, the wave function doesn't have such a deep meaning, right? What we actually detect are local observables built out of fields. And there, the mathematical structure of the theory is built in such a way that whatever weird things the wave function does, it cannot carry any data that I can actually measure. And I want to give you an example. There is the famous story of the tachyon field. The tachyon field is the hypothetical particle with space-like momentum that one wouldn't. Now, when you create the tachyon field, so the field whose excitations are tachyons, that's a perfectly causal theory. Nothing propagates faster than light. Indeed, it is believed that in any symmetry breaking, we form the tachyon field. It's an unstable field, but we can form it. It's perfectly causal. Why? Because, yeah, you have these, we can call them particles with space-like momentum, but you never measure you never detect the particle itself. What you detect is particular combinations of the field. And what you can show is that when you construct a localized perturbation to the field, this propagates inside the light cone. It stays inside there. And although maybe the individual tachyon you may think goes faster than light, you never get only one tachyon. You always get a combination of stuff in such a way that all these superluminal effects of the tachyon are not detectable. It's quite a magic thing, but it's one of those things where many people get confused.
I think I had my own confusion about tachyons. I read about them some long time ago, and when you mentioned, as you said, like, okay, you have the tachyonic field, you have tachyons, and they travel faster than the speed of light. And the first question comes to my head, as you said, what about causality? And then what you tell us now is the causality itself is not with the speed of light, moving the speed of light, is with the information transfer faster than the speed of light.
Yeah, you really need to imagine, what if I change? You shouldn't think about the tachyon itself. What you always need to have in mind when you talk about causality is the following question. If I take a physical system and I change something in a place, how does the change travel around? And what you can prove using the tachyon field, that nothing propagates faster than light.
That's very clear and very nice.
Yeah.
I think, I'm very happy with your answers. It's very clear, very simple, and I think our audience will be fascinated by them. Okay, so now moving a little bit closer to what you guys did, the collective excitation.
Yes.
In this case, I want to take the term and try to understand it. Like collective to me mean, we're speaking about the system. It's something happens collectively in the entire system. It's not particle by particle or one spot at a time. It's the entire system have some collective behavior. And excitation, maybe we can find some way to simplify that, but what's meaning to you in your research?
So I can try to give you the intuitive idea. The intuitive idea is you take a piece of matter and you disturb it. You may blow on it, kick it, irradiate it. Okay, you do something.
Okay.
When you do it, he's no longer in full thermodynamic equilibrium. Imagine that it was starting in thermodynamic equilibrium. You have generated waves, perturbations, things like that. Now, what happens is that just like in a field, you can find the particles as the excitation of the fields, the eigenmodes of the theory. You have something similar also in this case. You can create a list, you can really construct a list of all the possible ways in which the system responds, all the possible waves that you generate. In simple terms, you can visualize like this. It's called it's the spectrum of the theory. It's the spectrum of excitation of the theory. The technical thing is the singularities in the retarded correlator, these things. But as an intuitive idea, it's the waves.
In a simple way, it's basically you're looking to all disturbance happen in this matter.
Yeah.
After the effect. So like if I'm in a lake that has no waves and I throw a couple of like stones in it, it starts creating waves, and what you will be interested in is not the single wave, but the whole wave's propagation.
Exactly. So here is the interesting things. Every theory of matter possesses a list of these excitations. You can really make a list of them. Hydrodynamics has 5. So 2 sound waves, 2 shear waves, and 1 diffusion wave. But a microscopic theory, in principle, in the thermodynamic limit, so in the limit of a very big system, has infinite. Kinetic theory has infinite. Quantum field theory in general has infinite. Holography has infinite, and so on. So hydrodynamics only captures 5 of these, which are the so-called hydrodynamic modes. They're called like this. They are those that live that are supposed to live the longest. And then there are all those that one usually assumes die out fast, approximately. And so hydrodynamics has only a subset of those. Now, the big question is, can I assign a concept of causality to these waves, right?
Okay.
And that's a tricky question. That's a very tricky question. So here is the historical development of the topic. You work with the ideal fluid, so fluid without viscosity, there is no friction to the fluid. And then you generate sound waves, for example, and you discover that they travel at the speed of sound. Okay. What does it mean that they travel at the speed of sound? It means that the whole structure of the wave, imagine that it is a plane wave for simplicity. The whole structure of the wave just drifts without changing shape, without changing anything. It just undergoes translation, right, in space at the speed of sound.
Okay.
Now you put viscosity. It becomes trickier because now you can still create a little wave packet, no? Right? But now it also changes in shape. Okay, so if you describe the propagation using Navier-Stokes, what you discover is that the shape expands at infinite speed, in the sense that if you prepare a wave that is localized in a specific region. So remember what we were saying before about causality.
Yeah.
Causality is I need to know when the information about the existence of the wave reaches me. So I prepare a wave that is localized here, and right, a millisecond after, the wave is everywhere. Now, people were concluding from this, they were saying, well, come on, I mean, the Navier-Stokes equation is an approximation. It is a coarse-grained theory. It does not capture the modes exactly. It captures them at low wave numbers, so at small gradients. These things that propagate faster than light are an imperfection of the theory. And that is correct, okay? These tails of Navier-Stokes are incorrect, are an approximation of the theory, are an imperfection. But then here is the thing that we prove rigorously. In a hypothetical exact theory, where you are able to describe the sound mode exactly, so you have the exact dispersion relation, you know sound perfectly, exactly the same happens. You prepare a perturbation in density, because sound wave, is a density wave, right? You prepare a perturbation in density that is localized in a specific region of space. Fraction of a second, it's everywhere. Now, what is going on? Are we violating causality? Absolutely not. Why? Because what you discover is that this sound wave is only one of this infinite list of excitations. There are some excitations that are not captured by hydrodynamics, as I said. For example, there may be a chemical composition wave, right? If there can be a chemical reaction inside the fluid, I can create a wave in which the chemical composition changes and the fluid rearranges. Or I can create some anisotropies in the pressure, very strange, right? Some strange anisotropies. Or I have an infinite list of possibilities. Now, what happens is that whenever you try to create a density perturbation that is localized in this region of space, and you try to make sure that you have only a sound wave, then there will be outside of this region of space a perturbation in something else that is not the density, which may be, for example, the decomposition or anisotropies in the pressure that are already there outside, but they are not captured by hydrodynamics. So the point is, it looks like hydrodynamics is propagating information faster than light. But that information was already accessible within the microscopic theory from which hydrodynamics emerges. The hydrodynamic theory has its notion of what information is, because a hydrodynamic theory has its states. So when you specify the state of a hydrodynamic system, you specify its density, its velocity, its pressure, its, these quantities. You prescribe the conserved densities in general, the energy density and so on. Now, the point is that you do not specify other things like this weird anisotropies in pressure and so on. Now, what you discover is that the information that you lost in hydrodynamics was actually there inside the microscopic theory. And when you have the impression that the hydrodynamic wave is propagating faster than light, okay, there is no information propagating there, because that information was already there, but it was contained inside other features of the microscopic theory. So the microscopic theory contains all the information that hydrodynamics has lost. And it may look like the hydrodynamic wave is traveling faster than light, But it's just that there was something that hydrodynamics was not capturing that was there just waiting to push the density out.
I got you now.
Right.
Yeah, I think now it's
Yeah.
clear. Yeah. That's very interesting. So by the end, the main conclusion of the paper was like, okay, we guys was, I wouldn't say deceived, but was correcting our point of view. Nothing travels faster, or like information in hydrodynamic doesn't travel faster than the speed of light, rather than the information was contained already in the different modes of the hydrodynamics.
So exactly. So I think that the main point of the paper is, since causality is a statement about information, you need to specify information of what. If you focus only on the information contained within the structure of hydrodynamics itself, okay, it may look like some information traveling faster than light, but that information was already accessible within the microscopic theory. So hydrodynamics, if you want, since hydrodynamics implements a loss of information because it cares only about large-scale stuff, it cares about the small details. So it may look as if information is being pushed faster than light, but that information is in the small-scale theory, right? It was already there, but you needed to go and search for it in the small-scale theory. So in general, what happens is that if I am here in this location and I want to send a message, and I speak, I generate some sound waves. If I generate a sound wave that is localized only here, then I know that I'm not generating only a sound waves. I'm generating a sound waves plus a lot of other microscopic things that superimpose together in such a way that nothing reaches you faster than light. But if I want to describe a pure sound wave, then my attempt of localizing the density perturbation here generates portions of excitations outside the light cone always, which are, however, in the microscopic theory.
That's very interesting. No, I think
it's a very tricky and subtle topic.
I think you did a good job explaining, and I think now we had a clear idea about the paper, which will be in the description of the YouTube video when it gets posted. I think we covered most of the basics and what's the causality is, what's the importance of it. I think even me did learn a good portion of information today. And Lorenzo, at the end of this interview, I want you to speak to the students. So we have usually younger students from the Arabic world and sometimes from United States that listen to this show. And if you'd like to give them an advice about the academic future and career, we both have been going through that. I will be happy to hear from you.
Yeah, so I don't think I can give advice about how to survive in academia. So I think that the most powerful tool for a theoretical physicist that is usually, we don't really learn it in the university, but the most powerful tool is the thought experiment. Okay, if you are a theoretical physicist, that's the most important thing that you need to learn and to play with. So very often we are presented with a problem that is extremely complicated, that contains a lot of details, because nature is complex. I want to explain a certain physical phenomenon, and there are so many details out there that you may need to know to get it. To people that do, heavy ion collisions and the quark-gluon plasma are aware of all the complications that are left and right. Now, the thought experiment is the following. You start by telling in your head, let's assume that. Suppose that there is. Okay. Then you lay down all the data, all the pieces of information that you have about the system, and you try to remove them one at a time, trying to you look at you want to describe a phenomenon, you try to remove all those things that you don't think are crucial to reach that aspect of the phenomenon you're interested in. You remove everything. Okay, you remove this, you remove this. The goal is to simplify the problem so much that eventually you have a system that you can solve analytically without suffering over the calculations. Okay, it must become a toy model. Okay, something super simple. You remove everything. If you recover the phenomenon you're interested in, then you're okay. If not, then you discover that you eliminate something important and you put it back. Now, you keep repeating this procedure, and the goal is to finally arrive at something that can be stated in a simple thought experiment that doesn't even require you to really mention the real situation, right? Imagine a fun parallel universe where reality is simple and there are only two things, and that you can write a simple calculation with pen and paper in half a page. That is the beginning of understanding. Then you build on top of that. Then basically you do all the ugly calculations. But the point is just what I find really helpful for me. Remove all the ugly calculations. Whenever you feel that the calculation becomes bad, you say, oh, that's going to be tiring. No, because you're not going to learn from this. Okay. Stop there, remove, change something. It doesn't matter if in the end the picture that you have is really the original system. It doesn't matter. Change, remove, alter, create. Spend days just walking and thinking and imagining until you get something that you really feel is super clear and is super simple and it works. And that's the thought experiment. And from there, you do all the rest of ugly stuff.
That's very interesting. One advice I get, like I was usually interested in watching some other shows and stuff. I think it was Sean Carroll that mentioned that on his book. I think it was the circle cow or the round cow, that he was always say that physicists are fascinated, or at least try to solve everything in a round way. So give
the spherical cow.
Spherical calculation is very easy, and then it's like, okay, if you want to know anything about the cow, let's assume a spherical cow and solve the problem. It's
exactly, like but also yes, but also because very often when you do this process, you end up finding general patterns.
Yes.
That if you start digging, you may even convert into universal theorems. Okay, so for example, this general statement about the impossibility of creating the fact that the excitations expand outside the light cone, this thing that comes about just trying to make it work with simple scenarios. You think about Klein-Gordon, you think about other very simple systems, just the diffusion equation, you try to add little details. Always start from the simple thing and removing everything that is not needed.
Great. I think with that, we can conclude our very nice interview with you. I'm very fascinated by the idea, by your nice and sweet explanation. I hope it's not our last interview over here. I really learned a lot, and it was a very fascinating time. So I would like to thank you for sharing.
Thank you for the invitation and for the interest in our work again.
Thanks so much. And to all of our audience, I would like to thank them too for the time, and I hope we'll provide a useful information about some new research and maybe a different topic than what they are used to. And see you later.